So let me describe what are invariance principles, and I'll do this by giving some examples. The first example is the classical central limit theorem, which says, which as everyone knows, says that if you have n independent identically distributed random variables with finite mean and variance, then after appropriate normalization, the summation of the xi's looks like the standard Gaussian distribution. And here by looks like, I mean that the CDF of the summation of the xi's approaches the CDF of the standard Gaussian distribution. And CDF means cumulative density function. And the second example is the Berry-Esseen theorem, and it gives a quantitative form of the central limit theorem, and I'll set a special case here which will be of interest for us. And it says the following: if you have a norm 1 vector W in n dimensions such that each coefficient of the vector W is at most epsilon in magnitude, then the CDF of the random variable summation of Wi xi, where each xi is a random plus or minus 1 bit, approaches the CDF of the standard Gaussian distribution, and in particular the pointwise error between the CDFs of the two random variables is at most epsilon. And the third example is the invariance principle for low degree polynomials of Mossel, O'Donnell, and Oleszkiewicz. And here they assume that let's say you have a real valued multivariate polynomial in n variables, and moreover they have a quantitative constraint that no variable in the polynomial is influential, and this intuitively means that no variable dominates the value of the polynomial with respect to the other variables. And we can quantify this in a precise sense, but let's not worry about the exact formulation. And given the setup, their result says that the CDF of the polynomial P evaluated on uniformly random plus or minus 1 inputs is close to the CDF of the polynomial P evaluated on Gaussian inputs. And the error between the two CDFs depends on how you quantify this no variable being influential. And this is a great result, and it took some time to prove, and most importantly, it has some very crucial applications in computer science. For example, it was used in proving the majority stateless conjecture, and other results in voting theory and in computer science. Okay, so those are the main limit theorems, but what do I mean by pseudorandom invariance principles? And let me illustrate by looking at the Berry-Esseen theorem again. So here's the Berry-Esseen theorem restated, and the motivating question for me is whether or not we need full independence between the xi's for this statement to be true. Can we have some limited dependence or allow some dependencies between the xi's and still have the statement to be true? And there is a lot of literature in probability on studying exactly these kinds of questions, where you allow various correlations between the xi's and still show some form of limit theorems. But the theorem that we will look at here is somewhat recent and is also somewhat surprising to me, at least. And it says that the statement remains true even if you have only 1 over epsilon squared Y's independence between the random variables x1 through xn. And here by 1 over epsilon squared Y's independence or k Y's independence, I mean that if you look at any subset of variables xi1 through xik of k random variables in the collection, they are mutually independent of one another. On the other hand, if you look at larger subsets of k plus 1 or k plus 2 variables, there can be dependencies between one another. So this is a very clean and strong generalization of the Berry-Esseen theorem, but for me what's most interesting is that this statement is applicable to distributions which have much less entropy than what the original statement was applicable for. So in the original statement we needed full independence across the xi's. So the entropy was of magnitude was growing with n, but here you can have much smaller entropy. And there's a very nice quantitative version of stating this. In particular, there exist many distributions which are 1 over epsilon squared Y's independent and have support size at most n to the O of 1 over epsilon squared. And if you think of epsilon as a constant, these distributions have support size polynomial in n, whereas the original distribution had size exponential in n. So you move from an exponential size distribution to a polynomial size distribution and still preserve the statement of the Berry-Esseen theorem. And what's also important for applications in computer science is that these distributions with small support and k-wise independence can be computed efficiently. Particularly, you can write down this entire support in time, say in time polynomial in n and 1 over epsilon, and you can sample from these distributions also efficiently and so on. And similarly, we can ask if we can get similar generalizations of the invariance principle for polynomials. So here's a statement of the result of Mossel, O'Donnell, and Oleszkiewicz. And we would like to know if the statement holds true even if we only have some function of epsilon-wise independence between the variables x1 through xn instead of true independence. And unfortunately, we don't know the answer to this question for degrees 3 and higher even now, as in now. And but what we do know is that the statement is true if along with k-wise independence, you impose some special structural constraints on the dependencies between these xi's. And this might not seem like much, but this is still important because we again get wide class of distributions for which the invariance principle holds and with much less entropy. In particular, we again get a wide class of distributions whose support size is n to the poly 1 over epsilon, and you have the invariance principle to be true again. So if epsilon is a constant, you again have polynomial in n size as opposed to exponential in n. So there was an abstract view of the pseudorandom generalizations of the invariance principles, and let me now describe one application as to why this is interesting as well. So the application is to construct give explicit constructions of low discrepancy sets. So the starting object for us is the n-dimensional hypercube, which comprises of all vectors of length n and coordinates are taking plus or minus 1 values. And what we want here is a subset S of the n-dimensional hypercube that is equidistributed with respect to all hyperplane cuts. And what I mean by this is that I want for every hyperplane, the fraction of red points on one side of the hyperplane should be within an additive epsilon, or the fraction of points in the total universe that lie on that side. So in this picture, we want the fraction of red points on one side of the hyperplane to be close to the fraction of blue points in the on that side of the hyperplane. So as stated, this question is not that meaningful because we can take the set S to be the entire hypercube. But the catch is that whether or not we can do this with a set S that is of much smaller size than the entire hypercube. And even now the question is easy because the probabilistic method shows that if you take a random set S, random set of size n squared over epsilon squared, then it will satisfy this equidistribution property with high probability. And in particular, there exist very small sets which have this nice geometric property. But what we really want, so this construction is not particularly insightful or useful for applications in computer science and in other cases. And what we really want is an explicit construction of such a set S whose size is polynomial in n and 1 over epsilon. And what I mean by explicit, you can think of any reasonable notion of explicit. Give me a succinct description of the set, or more concretely, what I want is the set S to be efficiently computable. That is, I can write down the elements of S in polynomial time. And this is important for several reasons. And firstly, it's a nice, it seems a natural question in geometry, and it has important applications in complexity theory and algorithms. For instance, it would be useful in numerical integration. And it's also connected to many other geometric algorithmic questions, such as those in metric embeddings, etc. So why is the Berry-Esseen theorem useful for constructing low discrepancy sets? To see this, let's take a geometric view of the Berry-Esseen theorem. So say we have a hyperplane in n dimensions. For instance, the hyperplane just checks if the summation Wixi is less than t or greater than t. Then the Berry-Esseen theorem says that if I take a random plus or minus 1 point, then the probability that it lies on one side of the hyperplane is close to the probability that a random Gaussian vector lies on the same side. And similarly, the pseudorandom Berry-Esseen theorem says that this probability should be the same as the probability that a random plus or minus 1 vector, which is only k-wise independent, lies on the same side. And this is useful in the context of discrepancy because it suggests the following construction for the set S. Take S to be k-wise independent, where k is some function of, say, k is 1 over epsilon squared. And the proof that this actually works follows almost immediately from the pseudorandom version of the Berry-Esseen theorem that I described. And what it gives is a construction of an explicit construction of a set S with low discrepancy as described, as defined here, and size at most n to the some function of epsilon. In particular, if you think of epsilon as a small constant, the size is polynomial in n as opposed to being exponential in n. But this is still not the best we can hope for, and is still far from the best we should get. And the best explicit construction has the right dependence on the dimension n, but the dependence on epsilon is still far from optimal. And finally, we saw the version for Berry-Esseen theorem, and let's try to do something using the invariance principle of Mossel, O'Donnell, and Oleszkiewicz, and that will be to the construction of discrepancy sets for polynomial surfaces. So here, just as for the case of hyperplanes, we want sets which are equidistributed with respect to low degree surfaces. That is, I have a degree d surface in n dimensions, and I want the fraction of red points on one side of the surface to be close to the fraction of points in the total universe that are lying on that side. And once again, we want sets S which are small size. And the probabilistic method says that there exist sets which have size polynomial in n and 1 over epsilon. And the main question again is whether or not we can construct such sets explicitly. Give me a succinct description or an algorithm for generating elements of the set S. And just as for the case of hyperplanes, we can use the pseudorandom version of the invariance principle for polynomials to get an explicit low discrepancy set S for low degree surfaces with size roughly n to the some function of epsilon. In particular, the size is polynomial in n whenever epsilon is a constant. And this is still an exponential improvement over taking the entire hypercube, but it is still far from the construction given by the probabilistic method, which has size polynomial in n and 1 over epsilon. So let me now finish by describing. So I described some examples of pseudorandom limit theorems, and this view of pseudorandomness comes from their applications in computer science, and it will be great to see if there are wide variety of generalizations of classical limit theorem as in probability, such as those to multidimensional limit theorems and to convex sets and so on. And it will be nice to see if we can get pseudorandom versions of them. And the other kind of questions I'm interested in are explicit constructions of geometric objects, such as the discrepancy sets I described, and the current best constructions are not quite optimal. And at a more higher level, there are various important results in convex geometry and geometry which use the probabilistic method, and I'm interested in questions and obtaining explicit versions of such results. And finally, limit theorems from probability have recently found a lot of applications in computer science, and techniques from computer science have found I have given new proofs of limit theorems, and I think there's a lot of scope for exploring this correspondence further.